Hi, I'm Anders Löhr. I'm going to talk about staged sums of products. This is joint work with Matt Pickering and Nick Wu. Let's consider as an initial example the semigroup class in Haskell, which is here displayed with just the diamond operator, the semigroup append operator, that is a binary operation that is supposed to be associative. Now consider the type foo here, which is a product type with three components, a list of integers, an ordering, and a text. All these three types have semigroup instances in the Haskell base libraries. And if we want to define a semigroup instance for foo itself, there is an easy way to do that, namely by defining the diamond operator to be equal to this sappend foo function that I'm defining here, which basically just applies the already existing semigroup append operation on the three components pointwise. Now, let's make this a bit smaller and let's consider an example. If I'm applying sappend foo to these two example values, I can just apply equational reasoning, replacing the left-hand side with the right-hand side. So I'm getting this, and then if I apply the append operation in the way that it is defined for these three types, I ultimately get this result. Now, this is all fine, but it is specific for this one data type foo. But the idea that we've applied, namely that we lift the semigroup instances for the components to a product type, that applies to essentially every product type. And we can express this more generically by using a generic programming library, such as generics-sop. So in generics-sop, that is a library that has been introduced in a WGP paper from 2014. The types are represented as n-ary sums, which are written ns in the library, and n-ary products, np. And then you get conversion functions that can go from a Haskell value to such a sum of products representation and back. And you get lots of combinators that operate on these sums and product structures so that you can write generic functions in a type-safe and very concise style that really encourages code reuse. So let's look at how the semigroup append operation would be written using generics-sop and would look like this. So it's still rather short, but it looks very different from the other function. And nearly all the functions and types that you see on this slide are from the generics-sop library. In particular, on the type level, is product type here expresses that a type is generically representable and actually has a product type structure, so it has only one constructor, and this all semigroup constraint here expresses that all the components of the type have to be an instance of semigroup already. Now, in order to see how the definition works, let's look at an example again. So if we instantiate gsappend just specifically to the foo type, and then consider applying this to the same two example values again, then again we can apply equational reasoning. So replacing sappend foo immediately by the right-hand side of gsappend, we get this expression. And now we can look at product type from and see what that does. Product type from is provided by the generics-sop library, but it has slightly different behavior for every product type. It is a specialized conversion function that applies to single constructor data types and immediately maps them to a product structure. And the product structure, you can see like this, is looking very much like a heterogeneous list. So you can think of it as just a product of these three things, IIS, IO, and IT. And one property of these products and sums in the generics-sop library is that their components are always parameterized by a type constructor that is applied to every component. And by default, here you get the identity type constructor applied to every component, and that is this I. So you can think of this as being isomorphic to a product of just IS and O and T, which is exactly the structure of this foo type. So if we apply this product type from function to the two products that we have, to the two foo values, we get this. And then the next step to look at is at this czipWidth-np function, and that is essentially a zipwidth-like operation, but for these heterogeneous product types. And it takes this operation here, map triple I of the diamond operator, which is allowed to be from the semigroup class, that is what this proxy here expresses. And like a normal zipwidth, it applies this operation pointwise to the corresponding components of the two products. And if we do this, we get a single product where every one of the three components is an application of map triple I diamond to the corresponding components. Now we have to look at what map triple I does, but that is just a small, simple helper function that allows you to apply a binary operator to two values wrapped in an I constructor and gives you back something that is wrapped in an I constructor again. So it simply combines these two elements using diamond. So if we do this, we get this. And then finally, product type 2 is the converse of product type from, and takes a product of components that are all wrapped in this I constructor and maps it back to an application of the original foo constructor. And then we have this, and now applying the diamond operator for the components, we get the same result as in the function that was specific for foo that we originally defined. Now this is also very nice, but we can of course ask ourselves, what about efficiency? So if we apply a micro benchmark and normalize and consider the handwritten version as the benchmark and say this has cost 1, then we unfortunately discover that the generics-sop version is roughly 6 times slower. And this is because of the overhead in the conversions. And now it obviously depends a little bit on what kind of generic function you're running, but the overhead is always there, and it is always rather significant, unfortunately. Now, the standard technique towards optimization could be to rely on GHC's optimizer in some way, and there have been quite a number of approaches discussed in the past for doing so, but in practice all these are relatively unreliable, and in particular generics-sop is quite difficult to optimize because all these combinators that we are executing are recursive functions, and recursive functions are normally not inline. So we would like something else that is also ideally more reliable. And that's why we turn to staging, to typed template Haskell in particular. So what is typed template Haskell? Well, it is a little known typed subset of template Haskell. Template Haskell has been introduced at the Haskell Symposium in 2002, and it describes an untyped metaprogramming extension for Haskell, but with typed template Haskell, which actually goes further back to a Pepham 1997 paper describing meta-ML, you can, in a typed way, construct and use Haskell expressions at compilation time using two staging constructs, quoting and splicing. And this has been implemented for Haskell by Geoff Mainland in 2013, but it is not very widely used, in particular perhaps because there hasn't really been a big paper describing it, and there is relatively little documentation on it. But it is there, and it mostly works just fine. So what do we get from typed template Haskell? One thing that we do get is a typed quote construct. So if we have an expression E of type T, we can surround it in these quotation brackets, and then we get an expression of type code T. And the idea is that there's no reduction within the quotes. We're just building an AST that is representing this expression for a later use. And internally, actually, this code type is mapped to Q of TX of A, if you're familiar with template Haskell internals. But we don't care about this for the remainder of this talk, so we'll just look at code as if it was abstract. And then there is a splicing construct. So if you have such an AST of type code T, then you can splice it and turn it back into something of type T. And you can do that either within another quote to insert something into a larger AST, or you can do it at the top level to insert something into the current module. And if you do it at the top level, it in particular means that all the computation in order to evaluate the thing that you're splicing is going to happen at compile time. So that is a way to force certain computations to happen at compile time and to be able to rely on the fact that something is reduced up to a certain extent before it even reaches runtime. So splices and quotes cancel each other out. If you splice something, then the contents of the splice are supposed to be a quote, and if you splice a quote of E, then you get just E. So what we have done is we have developed a variant of generics-sop that's called staged-sop. And in staged-sop, you can again write a generic version of semigroup append. And it now looks like this. It's slightly different in the types. We have this quoted semigroup constraint here, which I'm going to talk about later. And we operate on code A values now rather than on A values. And we have S product type from here written in some form of continuation passing style. But apart from these minor differences, the overall structure of the function looks pretty much the same as before. Now, let's look again at what happens. So if we want to instantiate this staged semigroup append function to foo, we would splice the staged version on concrete arguments that are quoted. And now the interesting thing is that this is a top-level splice, and this can be evaluated at compile time without knowing the concrete values foo1 and foo2. And let's see as an example how that works. So if we apply sappend foo to foo1 and foo2 in this style, then it corresponds to this top-level splice. And now this is something that can be executed at compile time. And first we replace the SGS append with its definition, and we get this. And now we have to look at S product type from here. And S product type from looks like this. So this is slightly different from the normal product type from in that it uses continuation passing style. What it does is it introduces a case statement on this foo expression, and it introduces this as syntax, right? And there's only a single option. And once we've revealed the single option, we can take the continuation, apply it to the representation of our foo value, which is again a product, but now the components of the product are not wrapped in I constructors, but in C constructors, which is just a new type wrapper around code. So every one of the components of the product is a piece of syntax. And this representation is applied to the continuation and then spliced at this point. Now, if we look at the situation here, then S product type from is applied to this foo1, and then the continuation is all the rest, right? This lambda A1 arrow up to the end of the expression. So what will happen here is if we just replace this first S product type from, is we get this case on foo1, right? And then this A1 down here is going to be replaced with the representation of foo1, which is this product of codes. So this is what we get. And now if we do the same thing for foo2, we get another case, and A2 has also been replaced with this representation. And now we're at a point again where we can apply czipwidth, and that is essentially the same as before, only that now we are applying it with this map CCC operator of the quoted diamond operator. But again, we're going to look at these components pointwise and are going to wrap them together. So we're going to get a single product where every component is a map CCC application. And map CCC is like map III, just a helper function that helps you to combine two C values into a new C value by applying the operator in a sufficiently quoted and spliced way. So we get the code representing the application of the diamond operator to the three components. And as product type 2 corresponds more closely to the normal product type 2 by just taking a product of code values and producing code for an application of the foo constructor applied to its three arguments. So we get this. And now if we see that the top level splice here cancels out with this quote and rearrange everything, we get this piece of code. And interestingly, if we compare this to the handwritten version, then this is obviously equivalent, modulo basic desugaring. And this is one of the nice things that staged SOP allows us to do. We can very easily see that the intermediate representation, these products and sums, that they only arise at compilation time, that they're only present for stuff that happens at compilation time, and they don't occur in runtime code. So it makes it much easier to reason about the efficiency of these functions. And indeed, now, because we've already seen that the code is equivalent, if we look at the efficiency of the staged SOP version of this code, it is exactly the same as the efficiency of the handwritten code. So staged SOP, to summarize, is a variant of generics SOP, and we can reuse quite a lot. We can reuse the sum and product types because they're already parameterized over a type constructor. We just modify the conversion function so that the from function is now in continuation passing style producing something that where each component is wrapped in a C constructor, so every component is code rather than the identity, and the converse conversion function similarly. But then all the combinators for working with sums and products, they also apply. They just can continue to exist in the same way. One thing, though, that is needed is proper handling of class constraints and type template Haskell, and this is something we had to add. So let me briefly talk about this. So this quote of the diamond operator is an example fragment that occurred in the example function that we've been discussing. And we can ask ourselves, what should be the type of this? If the type of the diamond operator itself is semigroup A double arrow A to A to A. Now, one option is to just disregard the constraint and say, we get code of A to A to A, still with a semigroup A constraint. This is what GHC 810 does, but it turns out to be wrong, because intuitively it means that the semigroup constraint has to be satisfied at the moment that we form the quotation. But the formation of the quotation happens at compilation time, but the generated code is executed at runtime. These are completely different stages, and there are problems with respect to that. And GHC also doesn't handle this persisting that would be needed of the dictionary correctly. So this isn't quite right. Another option, if impredicativity was available, but it soon will be, would be to include the semigroup A constraint within the code. This would work, and it would be morally correct, but it is not first class. We have seen that in the type signatures, we sometimes want to talk about the constraints decoupled from the quoted value, and that's not possible in this style. So this is not quite satisfactory on its own as well. So our answer is to introduce a special constraint former quoted. And so the constraint here will be quoted semigroup of A. And that clearly indicates that the semigroup A constraint here arises within a quote and is ultimately needed to be satisfied when this fragment is spliced rather than when it is constructed. So this is implemented in a GHC branch, and a proposal to turn this into something that is really implemented in GHC will soon follow. So in the paper, there is much more. We have more examples of staged generic functions that all also compile to optimal code, or at least to very, very good code compared to what you would normally get from generics SOP. We also have a much more detailed explanation of this quoted constraint former that I've just been talking about. and we talk about related work. Let me just briefly mention, so far most related work has been about the SYB style of generic programming, strap your boilerplate. And Jeremy Yallop has been publishing a nice paper on how to do this in a beautiful way in a typed setting, but in Meta or Camel. And there are these template your boilerplate and geniplate approaches for Haskell, but they use untyped template Haskell. But I think we are the first who are doing staged generic programming with a sums of products approach. So the conclusions of this talk are that with staged-sop we can finally write data type generic programs at a very high level, retaining type safety, but also having a reliable performance without having to trust heuristics of an optimizer of the compiler. And the constraint handling improvements, these quoted constraints that we've identified, they are independently useful whenever you want to write something in a staged way that involves overloading, and is really not specific to generic programming at all. And while it is really wonderful that the generics-sop library is set up in such a way that we can reuse so much of the original library, and the staging approach that we've taken in this paper can also in principle be applied to other generic programming approaches. I've already talked about SYB, but also GHC generics would work by modifying the representation types that GHC generics has a little bit more drastically perhaps than in generics-sop. If you want to try this, you can look at this branch in the generics-sop repository, where there are also instructions on how to build a suitably patched GHC branch. Thank you very much.